Okay, let's continue with some properties of definite integrals. And I'm just going to give you some of these and give you an example. The first property says if the function is defined at x equal a, then anytime you integrate a function from a to a, it's going to equal 0. So no matter what the function, if you're integrating, if the lower limit and the upper limit are the same number, that integral is always going to be 0. And I could show you with area that, but I'm not going to. I'm just going to show you. Basically, if you integrate from a to a in terms of area, you don't have any width, so therefore you would not get any area. Now, if you reverse the order of integration, let's say you're integrating from a to b, f of x dx. Well, if you take the same function and integrate from b to a, you'll actually get the opposite. So the integral of 0 to pi x squared dx would actually be the opposite or minus the integral that you would get if you integrated from pi to 0 x squared dx. And then if f is integrable on the three closed intervals determined by a, b, and c, then it turns out that if you integrate a function from a to b, you can pick any number on the real line, number c, and you can actually break this up into two integrals where you integrate from the lower limit to c of the function and then integrate from that, I'm sorry, I've got these backwards, and then integrate from c to b of that function. So you go from a to c and then you integrate from c to b, and that's the same as integrating directly from a to b. So for example, if you integrated if you wanted to integrate the function 2x from 1 to 5, then just pick a number. I just picked the number 2 out of my head. So you could integrate it from 1 to 2 dx, or 2x dx, and then you could add to that the integral from 2 to 5, 2x dx. And of course, 2 is no magic number. I could have picked any number. I could have said, I could write that as the integral from 1 to 6, 2x dx, plus the integral from 6 to 5, 2x dx. So it's true basically for any number as long as the function's integrable can be integrated over those intervals. And then it says if you have an integral, if you're integrating a constant times a function, that's the same as the constant times the integral of the function. So if you're integrating 1 to 4 x squared dx, if you know that's 21, and someone says, well, I want you to integrate 5x squared dx from 1 to 4, well, then you know that's the same as 5 times the integral of 1 to 4 x squared dx. And since you know this integral is 21, then the answer would be 5 times 21 equals 105. And then also, if you're integrating from a to b, the sum of two functions, that's going to be the sum of the two integrals, definite integrals. So for instance, if you knew that the integral from 1 to 4 x squared dx is 21, and you knew that the integral from 1 to 4 square root of x was 14/3, then if you wanted to integrate from x squared plus square root of x using the same limits 1 to 4, then you could say, well, it's going to be the integral of the x squared function from 1 to 4, which I just told you was 21, plus the integral of the square root function from 1 to 4, which I told you was 14/3, and then if you add those together, you get 77/3. And of course, you can combine these last two together. So let's take the same two integrals, and this time, instead of just doing a sum, let's say we integrate 1 to 4 2 times x squared plus 3 times square root of x. Well, that's the same as 2 times the integral of x squared dx plus 3 times the integral of square root of x dx from 1 to 4. And then we know that this integral is 21, and we know that this integral is 14/3. So we would have 2 times 21 plus 3 times 14/3, and then just figure out what that is to get the answer. So those are some properties of integration. There's also a couple of other properties. If f can be integrated and is non-negative on the closed interval from a to b, then that integral must be greater than or equal to 0. Well, it basically says that if the graph is above the, well, actually it says if the graph does not go below the x-axis over that interval. Like for instance, if you look down here at this brown region, let's say you integrated from here to here in this brown region. If you look here, I'm trying to find it. All right, so that graph right there does not go below the x-axis. So what they're saying is this integral from here to here must be greater than or equal to 0, since the graph never goes below the x-axis. Okay, and then another example says that if two functions are less than, if one function is less than or equal to another function over an interval, then their integrals must have the same relationship. The integral of the first function from a to b must be equal to the integral of the, or must be less than or equal to the integral of the second function from a to b. Well, this makes sense because if you think about it, here's we'll say this is f, this one here is f, and we'll say this function up here is g. Well, notice if you go from, say, here, a to b, whatever a and b are, if you go from a to b, notice that f, this function, is always smaller than this g function. Well, if that's true, then when you integrate the f function from a to b, then it must be always smaller or equal to the g function. And if you think about it, it makes sense, because if you were to integrate this, let's give these real numbers. If this was 0 to 2, and let's say that this function is square root of x, and let's say that this function up here, is this g of x, is equal to x squared. Okay, well, square root of x is always less than x squared from 0 to 2. So if you integrated, since, let's see, where is it? Square root of x is always less than this function x squared from 0 to 2, then we know that the integral from 0 to 2 square root of x must be less than or equal to the integral x squared from 0 to 2. Okay, so that's basically all that says. All right, I'm going to go ahead and show you how to evaluate integrals using U substitution, but now we're going to do definite integrals. So these are going to be similar to what we did before, but let me show you the trick. Okay, so let's say that I wanted to integrate this function using the power rule. Well, I would let u be the 5 minus x squared, and then du would be minus 2x dx. So what I'd have to do is I'd have to multiply the inside by a negative 2 and the outside by a negative 1. I'm sorry, a negative 1, inside by negative 1 and the outside by negative 1, so that I can get this negative 1 in here. Now, once I do that, this is actually going to be du. This part's going to be du, and this is going to be u cubed, or another way to write that is u to the negative 3 times du. Now, you might notice that I changed the limits when I changed to u, because if you want to, you can leave the definite integrals. You don't have to switch them back to x when you're doing definite integration, as long as you change the limits of integration. Now, let me show you how I got these new limits. Now, remember, u is related to x, right? U is equal to 5 minus x squared. So here, x is 1 and x is 2. So if x is 1, to get what u equals, I plug 1 in here, and I get u equals 5 minus 1 squared is 4. So when x is 1, u is 4. So I replaced the 1 here for x. Here I replaced it with 4 for u. And then what about when x is 2? Well, when x is 2, I plug 2 in here, and I get that u is 1. So I replace the upper limit with 1. I replace the x equal 2 with u equal 1. Okay, so that's where the 4 and the 1 comes from. And then I can integrate this. Since this integrates to u to the negative 2 over negative 2, and this is a negative out here, the negative times negative is positive, so I'm just going to get 1 over u squared from 4 to 1. Well, if you evaluate this at 1, you're going to get 1 over 1, and if you evaluate it at 4, you're going to get 1 over 16. So basically, I'm going to get 1 minus 1/16, which is 15/16. Okay, so here's another one. Not sure what happened there, it just kind of popped up to the first page. But anyway, here's another one. I'm going to integrate from 1 to 4 this function. Well, if you look at some previous examples, you saw me integrate this as an indefinite integral. And so I had to let u equal this expression, and then du turned out to be 1 over 2 square root of x dx. Well, so what I needed, remember, is I needed to multiply the inside by a half. So I multiplied the inside here by 1/2 and the outside by 2, so that this could be written as u to the 10th du. So now that's u to the 10th du. But let's talk about the limits, and don't forget the 2. Let's talk about the limits. This goes from x equal 1 to x equal 4. Well, let's see where u goes. All right, u is square root of x minus 3. So if x is 1, u would be square root of 1 minus 3 is negative 2. So when x is 1, u is negative 2. Okay, now what happens when x is 4? Well, when x is 4, u would be square root of 4 minus 3, which is negative 1. So when x is 4, u is negative 1. So make those two changes there, and then you get, you can integrate u to the 10th, and you'll get u to the 11th over 11 times 2, and then evaluate this at negative 1, and you'll get negative 1 to the 11th. I went ahead and kept the 2 11ths just factored out until I'm done here. But evaluate u to the 11th at negative 1 to the 11th, and then minus evaluate this at negative 2. So I get minus negative 2 to the 11th. And you might want to grab a calculator to figure all this out, but basically I got that the answer is 4,094 over 11. So you don't have to switch back to the original variable. You can, if you do switch back, then you just keep the original limits of integration. Okay, let's do a couple more. This one, let's see, if I let u equal x squared, then du would be 2x dx. So what I had to do is multiply on the inside by 2 to make that be 2x dx, and then the outside by a half. And so now this is just going to be 1/2 times the integral du over u. Now, when x is 1, that's going to make u be 2, and when x is 2, I go up here and figure out that u is 5. So I'm just going to integrate this. When I integrate this, I'm integrating from 2 to 5, since I'm going to leave it in terms of u. So I'll get 1/2 times the natural log of the absolute value of u from 2 to 5. Well, again, I'm going to leave the 1/2 on the outside, and then just evaluate this at 5, so I get natural log of 5, and then minus this evaluated at 2, so I get natural log of 2. So 1/2 times natural log of 5 minus natural log of 2, and if you need to, you can get a calculator and simplify that. Okay, you take this one and try it as a practice problem and see if you can get the answer that I got. And then I'm going to go ahead and show you this one. If we integrate this from 0 to 1, well, the top is going to be, I'm going to let u be the bottom, and then du is actually going to be the top. So I'm actually just going to get du over u, which integrates to natural log of absolute value of u. But let's talk about the new limits. If u is e to the x plus e to the minus x, then when x is 0, then u would be e to the 0 plus e to the 0, which would be 1 plus 1, which is 2. But if x is 1, then u would be e plus e to the negative 1, or e plus 1 over e. So basically, the lower limit is 2, the upper limit is e plus 1 over e. And so when I evaluate this, I get the natural log of the upper limit, which is this, minus the natural log of the lower limit, which is 2. And then, if you need to get approximation, you can use a calculator. I'm going to go through this one real quick. X squared e to the x cubed. If you let u equal x cubed, then du is 3x squared dx. So you need to multiply the inside by 3 and the outside by 1/3. And then once you do that, 3x squared dx is du. And so you just end up with 1/3 e to the u du. And then if you let x be 1 and plug it in here, you're going to get 1 for the u value. And if you let x be 2 and plug it in, you're going to get 8. And so you end up evaluating 1/3 e to the u from 1 to 8. And that's going to be 1/3 times e to the 8th minus e. And that's it on evaluating definite integrals using u substitution. Got a couple more things I want to talk about in this section, so check that out on the next video.